This is Jim Schnabel dictating or giving you the third talk in a series on biochemistry written by Albert Lehninger, 7th edition. Today we're going to be discussing physical foundations. Last talk, number 2, we talked about the chemical foundations, the centrality of carbon to process, and the particular areas of bonding, the vast array of bonding that occurs in the biological systems. Today we're going to talk about the bioenergetics component in kind of a broad way. So when we talk about living organisms, they exist without any kind of equilibrium with their surroundings. It's a case of constant flux, exchanging matter and energy, which is an open system. We talk about closed systems if we're only extending or exchanging energy but not matter. Since biological systems exchange both, we refer to an open system which exchanges both matter and energy. The first law of thermodynamics talks about the conservation of a chemical change, that the form of energy changes, but the absolute amount remains constant. So the organism exists in an order at some cost to the surroundings, and as a consequence, the organism has to expend energy in order to create the order that gives it its living properties. So under a normal situation, you have what's called a dynamic steady state, where the body is existing in a form that exchanges matter and energy, taking energy, whether you are a chemotrope or a photoautotrope, and using either light and carbon dioxide from the surroundings, or breaking down a carbohydrate and adding oxygen to produce energy from it. So we talk about electrons flowing from higher to lower electrochemical potential, and we talk about the way that the organisms create energy. Plants, by and large, photoautotropes, capture light and produce carbohydrate, and autotropes, i.e. animals and certain higher cellular forms, will break down carbohydrates and produce energy from that. So we have broad definitions. So we talk about the delta G is equivalent to delta H minus temperature times delta S. Delta G is a free energy. So a spontaneous reaction has a negative delta G. Enthalpy refers to the breaking and formation of bonds in a reaction. This is a measure of the heat production. And then we subtract from that the temperature, which is usually given in Kelvin at 298 degrees Kelvin for base temperature, and the delta S is the entropy change, which trends towards positive value. So we have, in the case of every reaction, this equation will apply in order to make the reaction go to completion. Sometimes you need to couple this, and this is where enzymes come from. Enzymes lower the activation constant. We'll be looking at that in due time. So we also talk about endergonic reactions, which are energy requiring, and you have to couple this to a reaction that releases energy, and the combination it drives the process, and we call these exergonic reactions. So the free energy is found in sunlight and foodstuffs, and these are used by the organism in question to get the energy requirement that is necessary. So when we look at biological systems, we're looking again at the phosphoanhydride, ATP being a double phosphoanhydride, and which gives 7.3 kilocalories of energy on cleavage of the terminal phosphate ester to produce ADP and free phosphate. In a closed system, we have these reactions occur spontaneously until equilibrium is reached, and the equilibrium constant we give is a ratio of the compounds in concentration with the superimposed power written by the number of moles of reaction. So at equilibrium, the equilibration constant is equal to the multiplication of the products over reactants. And this is a simple way of looking at it. There are obviously nuances and intermediate steps which create some element of complexity to these free energy changes. And so the delta G naught is a characteristic of that. So because we can produce a reaction that looks at the baseline, which is the delta G naught right there, and then the addition of the gas constant times the temperature, the natural log, again, of the equilibrium constant is here. We can measure this and get these energy requirements, but we don't know anything about the kinetics or speed of reaction. Again, this will require knowledge of the intermediate elements that are applicable to the reaction. And these are, as I said, multiple steps, and they're going to require some element of sussing out of these reactants. So again, the goal is to lower this activation state. That you've got the reactants here, and then the activation energy is this much of free energy it's put in. And if you had a catalyst, whether it's a metal catalyst in non-living or organic reactions, a metal, for example, like magnesium, or if you used an enzyme, you can lower this activation energy, and this is a catalyzed delta G, and then the products are occurring here. So the uncatalyzed delta G is here, catalyzes here, and the net result is this this change of energy right there. So when we talk about catabolism, we're talking about degradative pathways which yield energy. Anabolism is synthetic pathways which consume energy. So we talk about anabolic steroids, for example. Catabolism, which is present in some biological systems that are basically working overtime. Metabolism is highly regulated to maintain steady state. We'll be addressing this. There's feedback inhibition, so these to maintain the equilibrium constant under given conditions of concentration and temperature, that the excess final product will build up, and you eventually get a steady state with the reactants and the products in a state of stability. And then information coding is a process, and we'll be getting into this more later. But information coding, at least in prokaryotes such as E. coli, is single-strand DNA. So the information is stored in these in the DNA, and then you can get preservation through generations. There's a high degree of fidelity from generation to the next. And to give an example, the E. coli genome has 4.64 million nucleotide pairs. So that is what I have to say about that, and we'll be getting together real soon. Thank you very much. Bye-bye.